Okay, I think we're ready. Let's see, is it time to get started? I think it is. Okay, welcome everybody. Like I said, it looks like our in-person group is dwindling a little bit, but glad to see all of you here and also those of you in Zoom. Just a little reminder before we get started. We've moved some of the office hours, as you may have seen in the announcement. Specifically, my office hours, I'm moving from Monday to Wednesday because I didn't have anybody show up. And I thought, I think they're probably just not working on this yet on a Monday. So I'll be having office hours tomorrow, 3:30 to 4:30. So anyway, you can check the page to see the updated schedule. Okay, any questions on logistics or anything like that before we get started? Okay. All right, well, let's dive in. Today, we're going to be doing just like a real kind of whirlwind tour of statistics. So we're not going to have time to go into a ton of details, but we want to touch on some of the really essential, critical things to understand for working with data. So we're going to be talking about statistical inference and hypothesis testing. And so we'll talk a little bit about the central limit theorem, show how useful that is. We'll talk about something called hypothesis testing, confidence intervals, and A/B testing. So check out this article. This is a Wired article on A/B testing, which has really kind of revolutionized how industries conduct their business. And these episodes are also really quite interesting illustration of how statistics is really informing policies and strategies today. Okay, so to get us started, let's do our imports. So we're just going to import pandas and NumPy and SciPy. And then from the SciPy.stats, we're going to import a number of different distributions that we will deal with today. And also this probability plot, and then our standard plotting import. Okay, so a little recap of what we covered, not last week, but the week before that, when we started talking about descriptive statistics. And we looked at some descriptive statistics like mean, standard deviation. So these are ways of summarizing quantitatively what a data set looks like. Today, we're going to shift gears and be talking about inferential statistics. Here, the goal is to learn about a population. We're trying to make inference about the population that the data was sampled from. Okay, and then we went over discrete and continuous random variables. So a discrete random variable can only take values in some discrete set, like 1, 2, 3, 4, 5, something along those lines. And its probabilities are described by a probability mass function, or PMF. And so we would say this function describes the probability that the random variable takes on a specific value. So f of k, we would write the PMF is the probability that that random variable takes the value k. So for example, the simplest discrete distribution is the Bernoulli distribution, where there are only two possible outcomes, either 1 or 0. So you can think of this as tossing a coin. You either get a 0 or a 1. So the PMF is going to equal P. So think of this as saying that the random variable equals 1 with probability P, and the random variable equals 0 with probability 1 minus P. Okay, so the mean of this distribution is P, and the variance is P times 1 minus P. And so when P is exactly 1/2, we think of that as a fair coin. So we can think that, about half the time we'll get heads and half the time we'll get tails. Okay, and then we also discussed the binomial distribution. What is the binomial distribution? The binomial distribution is obtained by essentially tossing a coin n times and adding up how many total heads you get. So it's basically the sum of n individual Bernoulli random variables. And it has a probability mass function given as follows, where don't worry, these are some constants, but it's a formula. It just tells you with what probability the random variable takes on its different values. In this case, the possible values of the random variable are 0, 1, up through n. Okay, so here we can do a little plot of the probability mass function. Let's go ahead and run this, of a binomial random variable. Oh, is that all right? So if we set n to be 10, we're going to do 10 trials or coin flips, and we're going to have a probability of 1/2 of a success, or of getting a heads in each flip. Then we're going to define this function f as the probability mass function of the binomial random variable. Then we can make a little plot just evaluating that function on its range of possible values, which is given by that. Now remember, the range doesn't include the last point, so that's going 0, 1, up through n. And then we're going to do a little plot of the probability mass function, and you can see kind of looks like a bell curve, right? It's got these discrete points, but they're kind of bell-shaped. Okay, so some facts about binomials, like I said before, it's just the sum of n Bernoulli random variables. And we think of this as summarizing the result of n independent coin flips. So what happens to the mean? Well, before, for the Bernoulli, I just had a mean of p. Now I have n of these things. So it's just n times p. And actually the same with the variance. The Bernoulli, it was p times 1 minus p. Now we have n of these things. So the variance actually just adds up. It's n times p times 1 minus p. Okay, and then the Poisson distribution is another one that you'll see in homework, but we won't go over that one in class. Okay, so continuous random variables are another class of random variables. And for these guys, they can take on any value in a continuum. So you can kind of think of them as potentially having an infinite decimal expansion. There's just all of these different possible values in any real value along some interval, say. And they have probabilities described by a probability density function, or PDF. And how does a PDF describe these probabilities? Well, it describes it in terms of the likelihood that the random variable lands in a certain interval A to B, and the probability that the random variable is in between A and B is given by integrating the PDF from A to B. So for example, the most famous example of a continuous distribution is the Gaussian distribution, and it has a PDF given here, where mu is actually the mean of the distribution and sigma is the standard deviation distribution, and it's just shaped like a bell. So sometimes we refer to this as a bell curve. Let's run this code and we can take a look at the picture. So here, let me go over the code real quick. I'm specifying a mean of 0, a standard deviation of 1, and I'm just making an array of x values, which range from the mean minus 4 standard deviations to the mean plus 4 standard deviations. So in this case, just minus 4 to 4, as you can see in the plot. And then I'm evaluating that vector. I'm evaluating the normal PDF function along that vector and then plotting that. So here we just have a plot of that PDF function, which is a nice bell shape. Okay. All right, so some facts about the normal distribution. The mean is mu and the standard deviation is sigma. So those show up explicitly in the PDF, so they're easy to read off from the PDF. And like we said, we calculate the probability of normal random variables being between A and B by integrating the PDF. To actually do this, it's useful to define something called a CDF, or cumulative distribution function. So usually we denote that with a capital letter F. So f of x is the probability of being less than or equal to x. And so this would just be obtained by integrating the PDF from negative infinity all the way up to x. So you're just looking at the probability of being below a certain value. Okay, so then we can rewrite, right, if we're interested in the probability of being in between A and B. If you remember a little bit of calculus, you'll remember you can rewrite that integral from A to B as the integral from minus infinity to B minus the integral from minus infinity to A, and that's just f of B minus f of A. So if we know the CDF function, all we have to do is do f of B minus f of A to compute the probability of being in that interval. So that's kind of handy because then we don't have to remember how to integrate. We just have to remember how to plug in values into a function. However, for the normal distribution, it's not a very nice function. The function is kind of only defined in terms of an integral. So you'll just use technology to do that, use Python, and it'll do it for you. Okay, so here, let's see. Oh yeah, here's the plot of the CDF function. Now, what do you think is going to happen? Actually, let me ask you this. What do you think is going to happen to the CDF function as you make x larger and larger? As x goes to infinity, what happens to the CDF function? What's that? Yes, and you know what that number would be? Yeah, one, I saw somebody say it, 1, indeed. It converges, it levels off, right? Levels off to just some number. That number is actually 1 because we're talking about probabilities, because we know that, you know, the PDF has to integrate to 1, which means the value of the CDF has to converge to 1 as x gets larger and larger. So we get kind of like an S shape. Okay, and this is just basically the same code for plotting that we did before, but now calling the norm.cdf function, evaluating it on our vector x. Okay, so let's discuss just a couple of quick exercises, how to interpret these quantities as probabilities. So if I have this right here, what probability is that representing? That's right. The probability that it's going to be between negative infinity and 1, probability of being less than or equal to 1. And here for my normal, which here is actually a standard normal because I used a mean of 0 and a standard deviation of 1, and that's like 0.84. And so you could read that off of the CDF plot. If you look at 1, and then you look at where this curve is, you follow it over here, that's 0.84. Okay, what about this next one here? Yeah, the probability of the random variable is between -1 and 1. And so this is, in this case, also telling us the probability of being within 1 standard deviation for a normal distribution, and that's 0.68. Okay, now what is this telling us? That's right. So we have, all values have to be between negative infinity and positive infinity. So with probability 1, you know, we take on a value between negative infinity and positive infinity. Right? It's not really telling us a whole lot other than this is a probability distribution. So it's integrating to 1. Yeah.
What does log represent in the CDX? Like,
oh, that's the mean. So the Python syntax, lock is the parameter for the mean. So I defined mu myself. So, you could put this in log equals 2 or log equals 0 or whatever. So first you say log equals whatever the mean is for the distribution. And then you say scale equals whatever the standard deviation is for the distribution.
Oh, so that'll just look
Yeah, so here equivalently, I could just say, because this is, I used 0 and 1, right? So,
It's gonna give you a different center at 0, standard deviation 1.
yeah, that's right. Yep. Right, and so this, indeed, yeah, and you can plug in infinity into there. So that's kind of cool. You can actually plug infinity as a value into the CDF function. And it won't yell at you. So that's nice. Okay, and then finally, what is this saying?
It's a probability in the points, and the cost is the interval is 0, so the width is 0, so it's 0.
That's right.
The area is
So it's saying the probability of any one specific value, in this case, the probability that the random variable equals 1 exactly is equal to 0. And this is a property of any continuous distribution, because you have, so many different possible values. The probability of any one specific value is always 0. And so that's why we describe these probabilities in terms of areas, like areas of little intervals. Okay, so you might think, well, why? Well, it's never going to be exactly 1. It's going to be like 1.000012458. Okay, that's never going to be exactly that. It's just any specific value will happen with probability 0. Okay, so all right, so that's kind of the recap of what we did before. So we're going to build on that, but move into statistical inference. We're going to start off with one sample statistical inference. A lot of times you have like 2 samples, maybe a sample from one population and then from a different population that you want to compare. That's really useful. But to start off with, we're going to keep it simple. And we have one population, one sample from that population. Okay. So there's some tools that require that a variable have a normal distribution. And so it's helpful to know how to check, does my data follow a normal distribution? So let's say we have a sample of data points, x1, x2, x3, and we want to know if it was sampled from a normal distribution. So there's a really handy tool that we can do to kind of get a visual assessment called a normal probability plot. It's a little confusing exactly what this plot is doing. Exactly what it's doing is sorting all the data in the data set to each data point, computing what percentile it is. That's the 5% point, that's the 10% point, that's the 20% point. And then it takes those percentiles and it looks up what the corresponding z-score would be for a standard normal distribution. So it's looking up, where those percentiles would fall for a standard normal distribution. And then it's plotting the data against what those z-scores would be for a standard normal distribution. And if that's a little confusing, that's okay. But the point is that if it's normal, that plot is going to make a straight line. And that's what you're looking for in the plot. So here in this code, let's say we have a sample size of 200. And let's look at taking samples from a few different distributions. The first one is normal distribution. And I'm taking 200 samples from this normal distribution. Here, my mean is 0 and my standard deviation is 1. That's what the log scale parameters specified. And then I can make this prob plot. I imported that. from the scipy.stats in the very beginning. And then I have to tell it to actually make this plot, not just to compute those values, and how to plot it. And I'm going to plot it with the PLT functionality that we imported. So this is the syntax that you'd want to use. Okay, and I'm going to do the same thing for a t-distribution, which we haven't gone over yet, but we'll just take a look. And then a Laplace distribution and a gamma distribution. Well, let's get some pictures here. Okay, so my first one, the data really was generated from a normal distribution. And so you can see when I make this probability plot, it's pretty close to linear. It's never going to be exactly linear. So it's helpful to take a look at what these plots look like, you know, for real normal data. So you get a sense of what kind of the expected little wiggles are. Let me run this again and you'll see how it changes. So if I run this again, okay, so now I get a little bit different deviations. So there's always some kind of going off the line, but it stays pretty close to the line. Okay, let's look at what the plots look like for some of the other distributions. This was the probability plot for the t-distribution. And what you'll notice here kind of happens consistently when you redo this simulation is that for the large values, these percentiles fall above the line that you would get from a normal distribution. And these down here fall below the line. So you might think, well, what is this telling us? Well, this is telling us that for the high percentiles are actually much higher in my data than they would be for a normal distribution. And the low percentiles are lower than they would be. So that's indicating, what do you think about the distribution?
It's more spread out.
Yeah, exactly. It's more spread out, heavier tails, exactly. So that's why those percentiles are like more extreme, both directions. You'll see a similar phenomenon here, right? Where we have this above the line over here, below the line over there. But it's a pretty symmetric pattern. So this is indicative of a symmetric heavy-tailed distribution. Okay. Now this one is interesting, right? Here it's different. Here we've got the upper percentile, the high percentiles are higher than what they would be, but so are the low percentiles, right? All of the, well, except for in the middle, those go below the line, but we see this sort of curving up shape. So in this case, what do you think? Do you think the distribution would be symmetric or not? What's that? Yeah, you're going to see a skew to the right, like if you would make a histogram of the data or plot its PDF function. Yeah, it's like skewed to the right. And so that means that your outliers or your really large points are your extremes are in the large values, not in the low values. And so that's creating this kind of shape where you see high points over here. Okay, so hopefully that's helpful. And the reverse would be true too. If it curved downwards, it would indicate that it was skewed to the left. Okay, but the main point, I know I probably went off on a little bit too much statistics there because I've taught a lot of statistics in the past. You don't really have to know all that. The main point is you can use this as a check for normality, and you're looking for a straight line pattern in the plot to sort of verify that the data has a normal distribution or is at least consistent with the normal distribution. All right, any questions on that before we move on to hypothesis testing? My Zoom people, feel free to also interrupt with a question or to put a question in the chat. Okay. Okay. All right, so let's then move on to hypothesis testing. This can be a little bit confusing at first if you haven't seen it before. How many of you have seen hypothesis testing like in a statistics course? A couple people, but not everybody. So, okay. So we'll definitely spend some time trying to understand the gist of this. To get started, let's kind of think about an example related to the coin toss. So let's say we have a coin and we want to know if it's a fair coin or not. Let's say maybe we just don't know, right? We don't know where the coin came from. We don't know if it's fair, but we are welcome to stand there all day and flip it, right? We can collect data about it. So we could flip it many, many times and see how many times we get heads, how many times we get tails, and then try to make some inference about whether it's a fair coin or not. So if we flip it a bunch of times, and about half the times we get heads, we might argue that the coin is fair. So the idea here is trying to make some kind of inference about what is that parameter P underlying this thing from data that we're collecting. We don't have access, actually, we can't flip the coin an infinite number of times. Okay, so let's simulate that in Python. So here F is just the binomial PMF. Let's say we flip the coin. Yeah.
What is like lambda?
This is just defining a function. So it's like a shorthand way of defining a function. We learned a longer syntax, right, with the def and the thing and the colon and the indentation. But these lambda functions are like, if the function is really short and easy, you can just do it in one line with this like lambda call. So this is saying, make a function f that's going to input k and output the binomial PMF evaluated at k. So that can be handy, but you could also write it out in the longer format, but this might save some time for like quick things you want to define. Yeah.
What does the lambda mean here?
Oh, so that's just how it's like a shorthand way of defining functions. So the lambda is just making it what's called a lambda function, which is kind of like a quick function definition to the best of my understanding. Okay, so first we'll create our range of values, and then let's plot this probability mass function for the binomial. Now here, because n was large, before we did 10, now we did 1,000. Now we have a lot of different possible values, right? So we see a lot of different dots showing up here in the plot. And here I'm also plotting one specific point, which is this point 545, and the probability mass function evaluated at 545. Okay, so that's kind of what let's assume that we do this experiment. We have a coin. We want to determine if it's a fair coin or not. So we flip it 1,000 times. And let's say when we do that, we're not actually going to do that. You're welcome. We get 545 heads. We can see what is the probability that this happens. What is the probability that we get 545 heads exactly? Well, it's pretty small, 0.0004, but that probability being small doesn't necessarily mean anything bad, right? The more different possible values you have, the smaller all the probabilities are, right? If you look at the peak of this thing, the maximum probability is of anything is only 0.025. So it's not necessarily, this is not really, whether this is large or small is not exactly what we want to quantify. We want to quantify what would be the probability of getting a value that's at least as extreme as that, okay? That's as extreme as that. So what's the probability that we got 545 or anything larger than that might be something that we're interested in. Okay, so let's just to read this because it's important. The important question is, what is the probability of seeing a value as extreme or more extreme than the value that we observed in our data? Okay, so here we might say that any result greater than 545 is as or more extreme. And so the probability of seeing an outcome as extreme as the one that we observed, we just want to add up all of these probabilities. So let's do that here. So we're going to sum these binomial probabilities, starting at 545 and going up to 1,000. And let's see what we get. Okay, we get 0.0024. That's the probability of getting a value anywhere along there. And then the complement of that, 1 minus that, 0.9975, is the probability of getting something smaller. Okay, now that is a pretty small probability, right? So we're saying if this coin were fair, there's only a 0.0024% chance or probability that we would observe a value this high above the mean, this extreme. And so that doesn't seem very likely. So it's possible, right? It's possible that this incredibly unlikely event occurred, or it's possible that the coin is not a fair coin. And so then you might make the inference that this seems to suggest the coin is not a fair coin because the likelihood of this happening is so small. Okay, in that way of thinking, we're just sort of looking at extremes defined in one direction, the extreme of being really larger than expected. But we might also want to define it in a symmetric way. You know, what's the probability that you are just far away from the mean, period, either really large or really small? And the equivalent condition for being too small would be less than or equal to 455, because that's the same distance from the mean. The mean is 500. And so if we want to quantify that probability, first, we can add up the probability of being greater than or equal to, first probability is the probability of being less than or equal to 455. Second probability is the probability of being greater than or equal to 545. That's S1 and S2, and then we can add them together. And so notice, right, they're symmetric because this is a symmetric distribution. So we get 0.0024 for both. But even if we take into account the probability of getting a really small value and add that together, we still end up with a probability that's only 0.0048. Still very unlikely that this would happen if we had a fair coin. Okay. It would only happen with probability 0.0048 if the coin really were fair. And the complement with probability 0.995, we would observe a value that's not that extreme. Okay, so it's very unlikely that if the coin were fair, we would see this result. And so this is the idea behind hypothesis testing. In hypothesis testing, we set up something called a null hypothesis. And in our example, the null hypothesis was that the coin is fair, i.e., that probability for each flip is exactly a half. And then you define an alternate hypothesis, which is just the logical complement of the null hypothesis, right? If the null hypothesis is not true, then what's the alternate hypothesis? So the alternate hypothesis is that the coin is unfair, right? That the probability is not a half, could be larger, could be smaller. We're just interested in anything that's not fair, that's not a half. Okay, so basically what you do when you're doing hypothesis testing is you just assume the null hypothesis is true. You don't know if it is, but you assume that it is. And under that assumption, that P really is 0.5, you calculate the probability that you would see something as extreme as what you see in your data. And if that is a really, really, really small number, then you say, well, that doesn't seem very likely. I'm going to rethink that this null hypothesis is true. Actually, I'm going to reject my null hypothesis because I don't think it's true, because it's very unlikely that what I observed would happen if it were true. On the other hand, if you assume the null hypothesis is true, you calculate that probability and it's pretty large, it's maybe 0.15, 0.3, then your data is consistent with that hypothesis, and so you can't rule it out. But a lot of times when people are doing data analysis, they want to reject the null hypothesis. They want to demonstrate, they want to get something that's a statistically significant result. So they want to get like a small probability in that calculation and reject the null hypothesis. Okay, so let's see. So this requires some kind of rule of thumb about what we consider to be a small probability and what we consider to be a large probability. In the example we just did, which was we got 0.0048, everybody agrees that that's a small probability, but some other cases are not so clear. What's often used as a cutoff is 1% or 5%. Those are typical values. So that if when you calculate the probability, you get something that's smaller than say 0.01, then you're going to reject your null hypothesis. Okay, so that's the idea. We set up a hypothesis, we collect a random sample, assuming the null hypothesis is true, we calculate the probability that we get a result as extreme as what we see in our data. And if that probability is smaller than our cutoff, we reject the null hypothesis. Okay, so a couple of comments here. Right, a p-value is, it's kind of like a conditional probability. It's a probability computed under the assumption that the null hypothesis is true. But it is not the probability that the null hypothesis is true. It's if the null hypothesis is true, what's the probability I see data like this? But it's not telling you the probability the null hypothesis is true. Is a little bit, just be careful in how you say it. Okay, the smaller the p-value, the stronger the evidence against the null hypothesis. Okay, and I think I just said that. It's not the probability that the null hypothesis is true. Right. Yeah, okay, I think I said all that. Okay, so what we have done up to this point is very distribution specific, right? We were talking about a coin toss, and because that's a pretty simple procedure, we actually have a function that tells us exactly what those probabilities are for flipping a coin 1,000 times. Normally that's not the case, right? Normally we don't know the exact distribution that we're dealing with. But the good news is we can approximate almost anything with a normal distribution. And so that doesn't really matter. And that's where the central limit theorem comes in. Okay, I think maybe this is a good point for a 5-minute break. Sound good? Okay, let's take 5 minutes, and it's 4:19. So let's come back at 4:24, and we'll keep going on this. But anyway, happy to answer any questions during break if anybody has a question. Yeah.
So when I was doing the I had a question that I don't know what context it came up in, but what
Okay, well, why don't we start back up again? I feel like today's lecture is a little bit long, and I am anticipating we're probably not going to get all the way to the end of it, but Thursday's lecture is short, so I think we'll have a little time at the beginning of Thursday to go over parts of this that we if we don't finish everything. Okay, so the central limit theorem, which is the most famous and the most useful theorem in all of statistics, So what does this say? It says that if we have a sample x1 through xn, a sample from some distribution, we don't know what the distribution is, but we do assume these are independent samples from a distribution that has a mean mu and it has a finite variance sigma squared. But other than that, it can be any distribution. So it's very general. In this case, if n is large, if we have a large sample size, then the theorem says if we add up all of the random variables, this is going to be a random variable. What's the mean going to be? Well, the mean is going to be n times mu, because we added up n copies of a random variable, each with mean mu. What's the variance going to be? N times sigma squared, again, because we had n of these, just like what we saw with the Bernoulli and the binomial. But more importantly, so it's kind of clear what the mean and the variance will be if they're independent. But the real punchline of the theorem is that this distribution is approximately normal, okay? That when we add up these random variables, they have an approximately normal distribution. And a really useful rephrasing of the exact same thing in the first bullet point is just to divide everything by n, because then we're looking at the empirical mean, which we will use, say, to approximate the true population mean. And then the theorem says if we add up all of the values and divide by n, so we take the empirical mean, this random variable is approximately normal with a mean of mu, right? So it's targeting the true population mean and a variance of sigma squared over n. And here we see the advantage of having a large sample size, because that means that variance is getting smaller and smaller. And so we're really able to estimate that mu well. Okay, so how are we going to use this theorem? I've hinted at a few ways, but let's see specifically how we're going to use it in the coin toss example. Okay, so what we did before, we were dealing with a binomial, but that's just a sum of Bernoulli random variables. And so we could also apply the central limit theorem, where each of these x's is a Bernoulli. And the CLT tells us that if n is large, the binomial random variables, the binomial random variable, because it is a sum, will be approximately normally distributed. So we could, approximate the probabilities, the resulting probabilities, like we did before, using a normal distribution, instead of explicitly having to know what the probabilities for a binomial distribution are. Okay, so this in general provides an easier way to do hypothesis testing. So let's revisit our question. How unlikely is it to flip a fair coin 1,000 times and see 545 heads? We're going to answer the same question, but we're going to use the normal approximation. So suppose we flip, now we're assuming the null hypothesis is true, that P really is 0.5, and suppose we flip that fair coin 1,000 times. How many heads do we expect to see? Okay, let's see what the CLT tells us. What do we expect to see? The CLT tells us that that sum, adding up all of the Bernoullis, is approximately normal with mean n times mu. In this case, that becomes n times p, 1,000 times 0.5, which is 500, and a variance of n sigma squared, which plug in that variance of a Bernoulli is p times 1 minus p, and you'll see that comes out to 250. Okay, so, and we can do a little experiment to see how good this CLT approximation is for these probabilities for the Bernoulli random variables. And so we'll call flipping a fair coin so 1,000 times and counting the number of heads we get a simulation. So we're going to run a lot of simulations and we're going to compare. So think about, okay, one observation from the distribution is flipping a coin 1,000 times and counting how many heads you have. That's one observation from a binomial distribution. Now we're going to do that a bunch of times. So we're going to do that 1,000 flips a bunch of times, and we're going to compare the distribution of what we get from that procedure with the normal bell curve approximation via the CLT. So let's see what that looks like. Okay, so first I can go through this code a little bit. Right, this bin vars, what am I doing? I'm just taking 10,000, right? So I'm taking 10,000 draws from this binomial distribution, where this binomial distribution is defined as the number of successes in 1,000 flips with probability 0.5. And I'm going to make a histogram of that data with the plt.hist. And then I am going to look at what the corresponding PDF is of the normal distribution with the same mean and variance. Okay, so mu n times p, sigma is the square root of np times 1 minus p. And I'll make my x's, and then I'll just evaluate this normal PDF with the mean given by the CLT and the standard deviation given by the CLT. And you'll see very close agreement, right? So it really does look like that this distribution is approximately normal. And this agreement will get better and better the more data that we collect, the more simulations that we run. Okay, and then we can take a look at the normal probability plot. It's very, very nice and linear. So we really see really good agreement between this binomial distribution for a large N and this normal approximation given by the CLT. Okay, so now let's compute the p-value of the hypothesis test using the normal distribution instead of the binomial distribution. So what is the likelihood of flipping a fair coin 1,000 times and seeing an event less extreme than 545 heads? Okay, so the CLT tells us this is approximately an event less extreme would be, the probability of being closer to the mean. So we would get that by integrating the PDF from 455 to 545, right? And so if we know the normal CDF, we would just subtract those values. Okay, so let's see what happens when we do that. Okay, we are having our mu, which is n times p, having our sigma as before, and now we're just saying the distribution of this thing is approximately normal by the CLT, so I can approximate the probability of being in between 545 and 455 by just subtracting the CDF values at those 2 points. And what is that probability? That probability of being there in the bulk of the distribution, the probability of being less extreme than what I observed is 0.9955. The probability of being more extreme is 0.0044. Okay, you guys remember what we got before? When we used the binomial exactly was 0.0048. Okay, so it's quite close. 0.0044 versus 0.0048, close enough. Okay. So this is a very general procedure. In general, you'll just calculate those probabilities using the normal CDF. Okay, so let's do an example. With the hypothesis test, it's helpful, I think, to do multiple examples so you can kind of see how these things are set up. So here's a problem. A common belief among the lay public is that body weight increases after entry into college, and the phrase freshman 15 has been coined to describe the 15 pounds that students presumably gain over their freshman year. Let mu denote the true average weight gain in the first year of college. we take the null hypothesis to be that mu is greater than or equal to 15. Okay, so that's this freshman 15 myth that the average weight gain across the whole population in the first year of college is 15 pounds. And so let's set up the null hypothesis to be greater than or equal to 15. We could also set it up to be 15, but we're going to set it up this way. So the alternate hypothesis is that the average weight gain in the first year of college is less than 15. So remember, the alternate is the exact logical complement of the null hypothesis. So if it's not greater than or equal to, it has to be less than 15. And let's use a significance level of 1%. I will say that's pretty conservative. A lot of times I see 5% as like a standard cutoff, but either way, it doesn't really matter as long as we understand the procedure. Okay, so now let's suppose we have a random sample. Maybe somebody did a study, they got a random sample of college students and they recorded their weight before and after that first year. And in this sample, let's say we have a sample of 100, actually this is real data from the journal Obesity. We have a sample of 137 students. And for these the sample of 137, the mean weight gain in the freshman year was 2.42 pounds. Okay, so they did gain a little weight, but they did not gain 15 pounds, like 2.5 pounds. With a pretty high standard deviation though, of 5.7. Okay, so now how do we do a hypothesis test? We assume the null hypothesis to be true. So we assume that mu is greater than or equal to 15. And let me, in this case, make the sort of clarification that actually here, when we actually compute the probability, we're going to assume it to be exactly 15, because we have to have a specific value in order to calculate those probabilities explicitly. So when you have a null hypothesis that's greater than or equal to 15 or some other value, you take that boundary value, you take the 15, and you use that in your calculation of the probabilities. Okay, well, as we will see in just a second. So we're going to assume if the null hypothesis is true, then that means that mu is 15 or even higher. So worst case scenario, so it's at least 15. So let's assume it's 15. How unlikely is it that we would observe such a small value in the sample, 2.42? Okay, so what does the CLT tell us about the sample mean? Tells us the sample mean, this empirical average, has an approximately normal distribution with mean, the true mean in the population, and variance, sigma squared over n. Okay, now that sigma squared is actually the variance in the population. We don't actually have access to that. We just know, well, what's the variance in our sample, but don't worry about that for now. The general procedure is just to approximate that sigma in the CLT with a sample standard deviation computed from your data, and that's what we'll do. Okay, so we take a normal distribution with mean 15, as stated in the null hypothesis, and variance, here we're using our sample standard deviation as an approximation of the population standard deviation, and then we square that, divide by sample size 0.2388. Okay, so then the p-value is the probability of seeing something this extreme, probability of seeing something as extreme as what we observed. We observed 242 to be even more extreme than that. You'd have to be even smaller than that. So we're looking at the probability that the empirical mean is less than 2.42. And so we have our PDF given by the normal distribution that we just integrate from minus infinity to 2.42. And let's do that explicitly. Okay. Okay, so and hopefully you're comfortable reading off this notation. What is that saying? It's very small, that's 0, okay? So this is scientific notation. It's this number times 10 to the minus 146. So anything with these e to the minus some number is going to be a pretty small number. Okay, so that's saying there's a practically, if the null hypothesis were true, if mu really were greater than or equal to 15, there's almost a 0% chance that we would collect a sample like we did. That's just very, very, very unlikely to happen. So more likely is that myth of the average of the freshman 15 is not true. Okay, so we're going to reject the null hypothesis and conclude that the freshman 15 is fiction. Okay, right, so the math here is not so bad, but it can be a little confusing just getting your head around setting up the hypotheses, what those probabilities really mean and what conclusion you draw. Any questions on that example? Okay. Okay. Okay, let's do another one. Zinc in batteries. So this is another example. Let's say we have a random sample, 51 Panasonic AAA batteries, and in our sample, we get a sample mean zinc mass of 2.06 grams and a sample standard deviation of 0.141. So does this data provide compelling evidence for concluding that the population mean zinc mass, like in all the batteries ever made, that if we looked at that mean, that it exceeds 2 grams, right? We see in our sample, it's bigger than 2, but it's not a lot bigger than 2. So can we say we have evidence that the population mean exceeds 2 grams, which is what the company claims. So let's see. So if the question asks, is there compelling evidence for ... that should be your alternate hypothesis. Whatever you're answering the question, is there compelling evidence for X? X would be the alternate hypothesis. So here, that the population mean zinc mass exceeds 2 grams, that goes into your alternate hypothesis. Okay, well then you know that the null hypothesis is the complement of that. So that's going to be mu less than or equal to 2. And let's once again take alpha to be 1%. Okay, so we know, according to the CLT, the sample mean has an approximately normal distribution with mean. This is once again one where the null hypothesis doesn't specify one value for the mu, but it's a less than or equal to, so we know it's 2 or smaller. So we'll say but we're going to take it to be 2 because that's kind of like worst case scenario according to the statistics we're computing, with mean mu of 2 and standard deviation sigma, or over the square root of n, which we approximate by s over the square root of n. Okay, so we could do this just like we did before, but I'll show you one variation on how to do this, which is just, it's really the same thing. So it doesn't really matter, but what people sometimes do is they standardize the distribution. So they will compute what's called a test statistic Z by taking the, say, empirical mean that they observed, subtracting the hypothetical population mean according to the null hypothesis, and then dividing by the standard deviation. So this is called standardizing, when you subtract the mean and divide by the standard deviation. And so that gives us a test statistic, which in this case comes out to 3.04. Why is this helpful? Well, it's just kind of helpful for interpreting how extreme your data is, because we know that the mu was 2 and the empirical mean was 2.06, but is that unusual? It might be a little hard to say. It doesn't really look that far away, but what this is telling us, it's reporting to us how many standard deviations away it is. And that's a more helpful way to think about it. So it's saying that under the assumption that the mean really is 2, as specified in the null hypothesis, what we observe is 3 standard deviations above the mean, which is actually kind of a lot, right? That's maybe a little more than you would think, looking at 2 to 2.06. But if you normalize it correctly, you see that's 3 standard deviations above the mean. Okay, so that's kind of helpful for interpretation. Okay, so in this procedure, what we've done is we've like normalized everything. So we think of this test statistic, we're going to compare it against a standard normal distribution. So assuming that the null hypothesis is true, how unlikely is it that we would observe such a large value of 2.06? So we can, that's our p-value, the probability of seeing something as extreme as what we observe. And basically there's 2 ways to calculate it. You can calculate it directly on the sample mean itself here, the probability that that's greater than or equal to 2.06, or you can standardize it and compute it, the probability that z is greater than or equal to 3.04, where now here z is going to have a standard normal distribution, whereas here the x bar would have a normal distribution with mean 2 and variance, etc. But it doesn't matter, you'll get the same answer either way you do it. So to illustrate how you would do it with the standardization approach, we would just integrate from 3.04 to infinity the PDF of a standard normal, and that comes out to 0.0012. Okay, so that's still pretty small, right? So what would we conclude in that case? Yeah, right. So we're going to reject the null hypothesis, which means that there's pretty strong evidence that the alternate hypothesis is true, that the mean really is greater than 2, that the company isn't lying, right? Okay. Okay. And here we can just see how we would compute that. This first line is computing it without computing the test statistic, without doing that standardization. So using a mean of 2 and the appropriate standard deviation, or equivalently, in the bottom, just do the normal CDF of the standard normal with your test statistic. Same answer. Okay, so let's do a little recap, little summary of hypothesis testing. And what we're doing is called a z-test, actually, because we're like computing this test statistic, which is, how many standard deviations away from what you expect, and then using a normal distribution to compute the probabilities. So that's called a z-test. Okay, so what do we do? Step 1, identify the parameter of interest and describe it in the context of the problem, right? If a problem says, is there evidence for X? X will be your alternate hypothesis, and the complement will be the null hypothesis. Choose a significance level alpha, usually 1% or 5%, and then find the formula. This is actually optional, depending on which way you do it, but find the formula for the test statistic. Like what do you see in your data? What is claimed in the null hypothesis divided by the standard deviation using the CLT. And then, and then one little comment, as we saw with the coin tosses, if the data is binary, so it's like a 0 or 1, and your alternate hypothesis involves a proportion, like what percentage of the population satisfies a certain characteristic, you can apply the CLT to a sum of Bernoulli's. And in that case, it's like a very similar procedure, but it's kind of interesting because now you're doing it on like categorical data instead of numeric data. But at the end of the day, you would look at like what is the sample proportion the proportion you see in your sample, what's the proportion that you claim in the null hypothesis, and then dividing by the standard deviation according to the central limit theorem. Okay, so those are kind of like the two main ways you would compute a test statistic for a z-test, one coming from when you have quantitative data and one coming from when you have some kind of categorical variable that you're studying with just two different values. So you're really looking at percents. Okay, so either way though, we compute that test statistic and we compute the p-value as the probability of being as extreme as what we observed. And then we compare that p-value with our significance level. If it's smaller than the significance level, we reject the null hypothesis and conclude there's evidence for the alternate hypothesis. If the p-value is large, then we can't say anything as definitive, right? So if you do get a large p-value, what does it mean? It means, well, the data doesn't contradict the null hypothesis. You know, it's kind of consistent with the null hypothesis, but it doesn't like verify that the null hypothesis is true. So if you get a large p-value, you have to be very careful in what you say. You just, you know, you can't say a whole lot. Okay, so when you're doing hypothesis tests, as you saw, I think the first one we did in the null hypothesis, we had equality, you know, that something equaled something. That's called a two-tailed test, right? We did one where we said p is equal to 0.5. And then our alternate was that p was not equal to 0.5. And in that case, that's called a two-tailed test. And we are interested in the area in both tails. We're interested in what's the probability that, you know, what we observed is more extreme in the sense that we might observe something that large or we might observe something that small. Okay, but sometimes, as we saw in the other examples that we did, we might do what's called a one-sided test, where the alternate hypothesis is just greater than or less than. If it's greater than, then you're calculating an upper tail probability, right? What's the probability that you're greater than what you observe in your data? And if it's a less than, then you're calculating a lower tail probability with the probability that you would get under the null hypothesis, something smaller than what you observe in your data. Okay, so just kind of might be always helpful to really write out the hypotheses clearly in the beginning and maybe draw the little picture so you know which probabilities exactly you're trying to compute. Okay. Okay, and then so this is valid as long as your sample size is large enough. And I'll just give you like some really ballpark cutoff, like maybe at least 20, okay? But if you have a really small sample, the CLT doesn't really apply because the CLT says for n large, it's a normal distribution, it's approximately normal distribution. But if n is small, it's not going to work so well, or it's not going to be so accurate to do a z-test. And there's an alternative called the t-test, which is better for small samples. Okay, so let's see. I don't think we really need to go into a whole lot of detail here, except that this distribution has a parameter, which is the number of degrees of freedom. And in the context of a hypothesis test, it would be sample size -1. The main thing to kind of know about it is, actually, we saw it when we did the probability plot in the beginning. We did the probability plot of the t-distribution. We saw it had heavier tails than the normal distribution, right? And that's kind of the main difference, is that it's like the normal distribution, it's nice and symmetric, but it's got heavier tails. And this is kind of accounting for additional uncertainty when you have a small sample size. Okay, so let's just take a look. So in this simulation, we're just comparing a normal distribution against the t-distribution with the sort of degrees of freedom chosen in the correct way according to the sample size. And then you can see, right, if my sample size is, sorry about that, I should have closed that, but it's a little late now. If my sample size is really small, you see there's a bigger difference between the t-distribution and the normal distribution. The t-distribution is really having these heavier tails. But as I increase my sample size, even up to like 20, which is not that large, you really don't see hardly any difference, which is why in practice, if your sample size is decent, doesn't really matter if you do a z-test or a t-test. Okay. Okay, so maybe those will probably be the last thing we get to, but maybe let's talk about the errors real quick, and then we'll call it a day. Okay, yeah, we're gonna have a bit of this to finish. This is, I found last year, this was just a lot to cover in one lecture, and that's fine. We'll spend a little more time on Thursday. But for our last thing to discuss today, let's talk a little bit about errors. So what are the errors that can happen when we're doing hypothesis testing? So remember, we either reject the null hypothesis if the p-value is small, or we don't reject the null hypothesis. So we think about, well, but what's going on in reality? Okay, in reality, we may have that the null hypothesis is true, or the null hypothesis is false. So this sort of, these columns are saying what is happening in reality. And then these rows are saying, what was our conclusion when we did our hypothesis test, right? So if the null hypothesis is really true, but we rejected it, that's an error. That's a type 1 error. On the other hand, if the null hypothesis is really false, but we didn't reject it, that's also not good. That's also an error, right? We would like to reject something that's not true. Okay, so those are the two errors. On the other hand, if the null hypothesis is false and we rejected it, good for us. If it's true and we didn't reject it, good for us. Okay, so the probability of making a type 1 error, here I should say, under the assumption that the null hypothesis is true, so assuming that we're living in this first column world, the probability of that happening is alpha. And so that's a little better controlled. We kind of have a sense of how likely that is to happen, to make that kind of error. The probability of making a type 2 error is actually quite difficult to quantify. So we're not really going to go into that. That's a little harder. But one thing that you can control is what alpha you choose when you do your tests. And it's going to vary from application to application what might be an appropriate value. And so let's think about what these errors mean in drug testing. So for example, if you're doing drug testing and you take the null hypothesis, in this context, is taken to be the drug has no effect on the disease, right? The drug did not cure the disease. The alternate hypothesis being that the drug is effective, right? The drug improved the disease. So type 1 error in that case would detect an effect that the drug cures the disease that is not really present, right? We found the drug to be effective, but the drug is really not effective. We just got lucky in the sample. On the other hand, a type 2 error fails to detect that the drug is effective when it really is effective, okay? So I guess a type 1 error we make when we sort of over pattern match, like we go overboard in seeing trends and patterns in our data, and a type 2 error we make when we, maybe are more conservative and we don't detect the effect. Okay, in the context of a trial, the null hypothesis is the person is innocent, and the alternate is that they're guilty. So a type 1 error would be convicting an innocent person, and a type 2 error would be letting off a guilty person. And so we can say, okay, well, what's worse? It would be worse to make a type 1 error. So we want to take a really small alpha in that context. Okay, I think we're out of time. Yes, but it's exactly 5 o'clock. I didn't go over. So, so we'll finish up discussing some of this on Thursday, and then also look at temporal data analysis. That's the next topic coming up. Any questions? Okay, great. Must have been just crystal clear. All right, have a great day, everybody, and I'll see you Thursday.
Yeah, with all this stuff, I just feel like I need to like work with it more.